The next topic we consider is the interaction of dislocations with point defects. As we know that dislocations have long range elastic stress fields, and point defects are associated also with certain kind of stress fields, because typically any point defect, even if you consider substitutional atom, will be different in size as compared to the host atom and will therefore result in a stress field. In these cases, of course, we have to differentiate the stress field of a substitutional atom from that of the interstitial atom. Typically substitutional atoms have a spherical distortion field, while interstitial atoms, which is in interstitial voids, have, apart from a spherical component, certain shear component also associated with them. This implies that point defects can actually interact with the elastic stress fields of a dislocation, and this interaction can lead to certain kind of segregation or certain kind of attraction to start with. So, defects associated with tensile stress are attracted towards the compressive region of the stress field of an edge dislocation. And as I pointed out, screw dislocations have only a shear stress field, and therefore, if a defect has a shear stress field, it can interact with the shear stress field of a screw dislocation. Otherwise, if the stress field of the defect is purely dilatational or hydrostatic, then it cannot interact with the screw dislocation. The solute atoms therefore can actually segregate to the core region of an edge dislocation and can lead to the formation of an Quatrille atmosphere. So, this kind of an higher concentration of the solute elements in the region of the core of the dislocation is called a Quatrille atmosphere, and this Quatrille atmosphere has important implications to the behavior of the material when you load it in tensile stress. That means, if you plot a stress strain diagram in the absence of these solutes and in the presence of these solutes elements, then there will be considerable difference, and we will take up the difference very soon. The reason that we need to, the main important difference, you will see that we actually require higher stress to move the dislocation once there is a segregation of the dislocation to the core of the dislocation, because now the segregation would mean that the system has gone into a lower state of energy, and if I have to pull the system out of this energy well, then I have to apply a higher stress. And in this case, as we know, to move a dislocation we need to apply shear stresses at the atomic level. Also, we know that the dislocation core is associated, especially if you are talking about an edge dislocation and the region just below the half plane, then that region is a region of extra volume or a free volume, and therefore, that region can nicely accommodate certain small interstitial atoms as compared to the normal lattice, wherein you require a certain higher energy to accommodate the interstitial atoms. An important example of this case of these interstitial elements is the non-spherical distortion field of the BCC carbon atom in BCC ion, and this can interact with screw dislocations, and as we shall see that this kind of a segregation of these carbon atoms in BCC ion leads to an alteration of the shape of the stress strain diagram. Now, let us start with an interaction of vacancies with the stress field of the edge dislocation. So, in the figure below you can see that actually I am showing the sigma XX stress field around an edge dislocation. So, the dislocation line is into the plane of the board right at the center here, and so let me mark that. So, this my edge dislocation is right at the center, and you can see that the entire half space above is tensile in nature and the entire half space below is compressive in nature. So, this is my compressive stresses below and my tensile stresses are above, and we know that this complete half space being tensile or compressive is in the case of edge dislocations in an infinite medium. If you have a finite medium or certain other possibilities, then this kind of a beautiful picture which is very symmetrical. There is a top down symmetry, that means a symmetry that the top half space is compressive, the bottom half space is, or in this case, tensile and compressive, and you also have the left right symmetry would be broken in certain other cases. Now, what happens to vacancies when they are present very near or nearer edge dislocation? They actually, as you can see, that vacancies are associated with tensile stresses, and they are therefore attracted to the compressive region of the edge dislocation. That means that suppose I have a vacancy sitting here, then it will tend to move towards the compressive region. That means it will tend towards us because there is a gradient in the stresses, and it can lower its energy as it moves towards the core of the dislocation or towards the dislocation line. The behavior of smaller substitutional atoms is also similar to that. Now we are talking about substitutional atoms smaller than the parent atoms, is also similar to that of vacancies. Larger substitutional atoms will be associated with compressive test field, and actually they will be attracted towards the tensile region of the dislocation. And if you are talking about interstitial atoms, and they are also typically interstitial atoms, as you know, are larger than the voids in which they sit. Typically we have seen that in FCC crystals, for instance, the voids are the tetrahedral and the octahedral void, and these interstitial atoms are typically larger than those voids, and therefore they are associated with compressive stress fields. Apart from, as I told you, there can also be some shear stress fields, and therefore these interstitial atoms are attracted towards the tensile region of the edge dislocation. So and they are repelled from the compressive region of the edge dislocation stress field. So let us look at the complete picture for vacancies, revising it. So vacancies are attracted towards the compressive regions, are repelled from the tensile regions, and you know there is a zero line of stress field right at the middle, for instance, and there is only one single zero line when you are talking about an edge dislocation in an infinite medium. So if a vacancy sits on this dislocation line, suppose I am talking about a vacancy sitting right at this point, then it will not interact with the dislocation stress field. In other words, it will remain unaltered, it will not feel the force of the dislocation. So in a sense, this elastic interaction between a point defect and a dislocation stress field can lead to attraction or repulsion, or in very special cases no interaction also, and this attraction or repulsion can actually lead to an assisted diffusion of these point defects towards or away from the dislocation. And the most important case of this is a case wherein there is an attractive interaction of the solute atoms of carbon towards the edge dislocations in BCC iron. So that is a very important example. So if I write down the character table of the kind of point defect on the left hand side and the kind of interaction with them, so we can see that a vacancy is repelled from the tensile region and attracted towards the compressive region. An interstitial atom behaves right in the opposite way, it is attracted towards the tensile region and repelled from the compressive region. A smaller substitutional atom behaves similar to the vacancy and is repelled from the tensile region and attracted towards the compressive region. A point defect which is larger than, which consists of larger substitutional atoms than the host atom, is attracted towards the tensile region and repelled from the compressive region, and in this sense it is similar to an interstitial atom. But as I told you, there is a fundamental difference between interstitial and substitutional atoms, that the distortion field of an interstitial atom might have a shear component, and hence it can also interact with screw dislocations typically. So what happens when I have, for instance, a carbon atom solid solution in BCC iron? So what can happen is that these interstitial atoms, the carbon, can actually segregate to the core region of the dislocation and preferentially come and sit in this region. Of course, we are seeing one atom here, but what we mean is that along this direction into the plane of the slide, lot of atoms can come and sit near the core of the dislocation, and this is what which I pointed out is called the Quatro atmosphere. So there is an atmosphere of these atoms around the core, in the core region of the dislocation, and overall this results in the lowering of the energy of the system, because now the tensile stress field, if you go back to the character table, the compressive stress field of the interstitial atom will cancel the tensile stress field of the dislocation, and therefore you will have a lowering of the energy. And now if I, what is the signature of this on the stress strain diagram? Now suppose I do a stress strain diagram, for instance, in aluminium. So let me draw, for instance, a typical stress strain diagram of aluminium. You would notice that pure aluminium, for instance, or commercially available aluminium, then you would notice that the curve will go up straight and then will keep going up, and this is a true stress, true strain diagram. But if you look at carefully at this diagram, which is for now for the example of a material like BCC iron with carbon and the clear cut signature is seen in a phenomenon known as the yield point phenomenon. In the case of aluminium, for instance, which I draw here, the material will show an elastic region, and then it will slowly the curve will bend, and that means that dislocations are moving and continuing to cause plasticity. In this case, what happens, even though if you look at this overall curve, you will see, you would have guessed that the material should start yielding somewhere here, but because of this Quadrille atmosphere, you need to apply an extra stress which is up and above this stress from here to here. Suppose I call this point A and I call this point B. I need to, or this point B is actually the upper yield point. I have to apply this extra stress so that, and this stress of course at the microscopic level can be drawn like this on this diagram. So this extra stress has to be applied so that this dislocation can break free from the Quadrille atmosphere, and of course repeated locking in this atmosphere can lead to a phenomenon known as serrated yielding. So, there is a serrated yielding, and once the dislocations are free of this Quadrille atmosphere, then they can this stress strain diagrams looks rather smoother. So, the entire presence of this yield point phenomena is because of this interaction of dislocations with the point defects, in this case carbon in BCC iron. So, to summarize this slide, if I were to take a pure iron material and shear it, then typically it will yield at stresses which are somewhere around A. That means the elastic to elastic plus plastic transition would take place at lower stresses. Now, because of the interaction presence of carbon, the carbon is attracted towards the lower half of the edge of this extra half plane. In other words, regions of higher free volume right here, which is now in the tensile region of the edge dislocation, and this segregation by diffusion can lead to the Quattrille atmosphere, which implies that now I need to apply extra stresses above and above what I would expect normally for a pure material, and therefore, this leads to an yield point phenomena, which is nothing but the locking of the dislocation by the carbon atoms. So, this is an important effect we are seeing, the yield point phenomena coming purely from this interaction of an edge dislocation with point defect, which is the interstitial atom of carbon. Dislocations can interact with, as I pointed out before, can interact with any one of these long range stress fields, and one important interaction is the dislocation precipitate interaction. So, some of these interactions are very important, because we start off with a material. If you say take a pure material, a whisker, which is 100% free of dislocations, we know that we can expect yield stresses of the order of theoretical shear stresses. Presence of dislocations weakens the crystal, and therefore, we have to find mechanisms by which we can strengthen the crystal. One of the mechanisms is to actually add substitutional alloying elements, which can actually raise your lattice friction, and therefore, in other words, give you a strengthening effect, which is called a solid solution strengthening. Interstitial atoms will also give you this kind of a solid solution strengthening. The other mechanism which is very popular is the precipitation hardening mechanism, in which you produce precipitates in a material, and these precipitates can give you a hardening effect. So, let us try to understand how the hardening effect of precipitate comes about, and more importantly, what is the dislocation precipitate interaction that we are talking about. So, precipitates are of three types. So, we have three types of precipitates out here, and the coherent precipitate is a precipitate in which the atomic planes are continuous from the matrix into the precipitate. In a semi-coherent precipitate, there are regions in which the atomic planes are continuous, and there are regions where the atomic planes ends at the interface, and that it can be interpreted as the presence of an dislocation. And if we are talking about a precipitate which has a dilatationally or which has a lattice parameter larger than the or larger or smaller than the matrix, then typically these would be edge dislocations or edge dislocation loops in the around the interface between the precipitate and the matrix. Therefore, there are coherent precipitates where planes are continuous, semi-coherent precipitates which are associated with regions of continuous planes and also with the presence of interfacial misfit dislocations, and there are incoherent precipitates wherein the atomic planes do not continue from the matrix to the precipitate. So, the mechanism by which a dislocation interacts with these kind of precipitates is differs depending on the kind of precipitate we are talking about, and one important point about coherent stress precipitates is that they are also associated with long range stress fields. That means, because there is a misfit in lattice parameter between the matrix and the precipitate, there is a stress field, and therefore, you have a stress field of the dislocation can interact with the stress field of the coherent precipitate. And as far as the normal stress interactions, they remain identical as far as the coherent precipitate. Like if you have a tensile region, it will be attracted to the compressive region. If you have a compressive region, it will be attracted to the tensile region, and therefore, there is no difference in that aspect. But as far as the dislocation interaction with a coherent precipitate goes, it could be very different from that as the way a dislocation would interact with a incoherent precipitate, and we will take up these two examples by the kind of mechanism by which they would interact. An important point to be noted is here, even though I said that there is an interfacial misfit dislocation present in the case of a semi-coherent precipitate, we are not dealing with the interaction of that dislocation with the precipitate, what we are talking about is a dislocation which is present in the matrix far away from the interface, which is now moving towards the dislocation and trying to interact with this precipitate. But in this set of lectures, we will only consider the interaction of a dislocation with a coherent precipitate and with an incoherent precipitate. So, what is the essential difference between a dislocation interacting with these two kind of precipitates? In case of a coherent precipitate, the dislocation actually can glide through the coherent precipitate and which will actually shear the precipitate. Now, why can it glide through? Because atomic planes, as I said, are continuous from the matrix to the precipitate, even though they are distorted. In case of an incoherent precipitate, the dislocation cannot glide through the precipitate, it has to bow or bypass the precipitate, leaving certain loops in the wake of the moving dislocation. So, we will take up these graphically so that we can understand these two interactions in a better fashion. The important point to be noted is that both these processes lead to need a higher application of stresses typically, and of course, I am assuming that the precipitate is typically harder than the matrix, and this will lead to the strengthening of the material. So, precipitation hardening or precipitation strengthening is a very important mechanism by which a material can be hardened, and therefore, you can sort of increase the strength of the material as compared to the weakened state because of the presence of dislocation. Now, suppose I have a precipitate lying on the slip plane, and now this is a coherent precipitate right here sitting on the slip plane, and now I have a dislocation line which is shown in blue moving on the slip plane coming closer to this precipitate. Now, I can actually see this precipitate on the side view, wherein I have the dislocation line here, and the dislocation is moving towards my right into the grey colored precipitate. So, what is going to happen? Since it is a coherent precipitate, the planes are continuous from the matrix to the precipitate, even though, for instance, this were an atomic plane, for instance, this could get distorted in the, and it could be still continuous. So, this is a typical kind of an atomic plane within going from the precipitate to the matrix. So, when this dislocation moves through the precipitate, the section of the dislocation, for instance, suppose now it has reached this stage wherein I have a section of the dislocation lying in the matrix and there is a section lying within the precipitate. The section of the dislocation which lies in the matrix would feel a different resistance to motion as compared to that which lies within the precipitate particle, because now the precipitate particles could be elastically harder and would therefore be difficult and would have a different Pearl stress, and therefore difficult to move a dislocation within the precipitate. Now, what happens when this dislocation leaves the precipitate is it creates a small step of Burger's vector B. So, within the, it means the particle has now been sheared, and therefore it leaves a Burger's vector in its wake. Now, this means that the surface area of or interface area of this precipitate has increased, and therefore that would require a little extra energy, and which would in terms in other words show up as extra stress which we need to apply to move the dislocation. But in any case, the section lying within the precipitate would face a higher what you call Pearl stress to move the dislocation, and therefore you will see a hardening effect even in the presence of the even though the fact that the dislocation is actually gliding through the precipitate. Now, of course, this is now so far ignoring the long range stress effects, but there will also be interaction of the stresses of the dislocation with the precipitate. Now, suppose I am talking about an incoherent precipitate, and therefore I come to a different kind of mechanism by which a dislocation can actually interact with a incoherent precipitate. So, now suppose I consider incoherent precipitate, and let me start with this diagram on the right hand side here, wherein I can see that these two grey spheres or grey circles are the incoherent precipitates, and this is my dislocation line shown in red, and this dislocation line is now, for instance, this is my dislocation line here, right here, and this is now pinned at these 2 points, because if I am talking about a precipitate here, for instance, and my dislocation line moving, it cannot move into the precipitate as it is incoherent. There are no continuous planes. So, in other words, it is as if a different crystal sitting across the interface. Therefore, the dislocation gets actually pinned at these 2 points, and therefore it cannot move at those 2 points. Now, suppose I am applying an external shear stress, the stress would be felt at all the points along the dislocation line, and these stresses would tend to bow the dislocation as shown in the figure on the right hand side. But if I bow the dislocation, then the length of the dislocation line is increasing. That means the energy associated with dislocation per unit length is also increasing. Of course, if I started off with a pure edge dislocation, now this dislocation would have a certain screw component to it. That means only one point would remain edge and the remaining would become screw. Or if I am starting with a pure screw dislocation, then I can similarly argue that this curved dislocation has a mixed character. Now, applying this external stress, the external stress suppose has a value tau, it will try to balance the line tension, the origin of the line tension being the increase in energy associated with the dislocation line, which goes as Gv square per unit length of the dislocation. Now, suppose I keep increasing the stress, then what would happen is that the dislocation line would bow more and more, the segment which is unpinned, the segment which is free to move would in an increasing stress lead to larger bowing. The upper limit for this radius would be the radius wherein this becomes a semicircle, and entire process starting from figure, for instance this point 1 to 2 to 3 will take place uphill in stress, because now I am increasing the dislocation line and therefore I have to counteract it with my applied stress, and therefore I need to apply an additional stress to cause this semicircle. But beyond this semicircle, now if I look at figure 4, this happens from beyond, from point 3, figure 3 would take place in downhill in stress, and what would happen is that this dislocation line will take a shape as shown by this lighter blue line on this figure here. So, this figure here, you can see that it takes a shape like this, and if this segment has a certain sign of the dislocation, suppose this is positive, then obviously this segment would have a negative sign, and therefore they would be attracted towards each other. At each point we have to remember that the line tension and the applied stress are opposing each other, and of course this is now going downhill stresses. And finally, if the final picture would be this picture 5 as shown here, in which case you will have a original line segment retained, but additionally these two segments, the positive and negative, would come and cancel each other, and this dislocation would take a circular shape which would give it the equilibrium configuration. So, because that would be the for a given length of segment, this would be the what if I increase or cause any dents in this, that will lead to an increase in length of the dislocation line, and therefore this is the configuration we would adopt of the lowest energy. And so at the end of this whole process of shearing, I would notice that I have a dislocation line segment which I originally started off with. So you can see this is my original line segment which was pinned between A and B. So I have this my A and B pinned segment remaining, but I have additionally created a dislocation loop. This mechanism, as I pointed out, is called the Frank-Reed mechanism, or the Frank-Reed double source as it is called, double-ended Frank-Reed source, and this is creating an additional loop. That means as the same set of same dislocation pinned segment can keep on operating again and again, creating such kind of loops. So again I applied shear stress, then this whole process of bowing of the dislocation line can, but now we have to remember this bowed segment has to interact with the stress field of the additional loop which has been created. That means the second time I operate the same loop, same pinned segment, to operate a double-ended Frank-Reed source, I have to apply an additional stress as compared to the first time around. But nevertheless, I can keep on operating this Frank-Reed source and therefore create more and more loops. So we have seen that. So this is just an example of an interaction of a dislocation with incoherent precipitates. There may be other important ways in which they can interact, but now we just consider two examples, one for coherent precipitates and one for incoherent precipitates. So let me summarize this dislocation precipitate interaction briefly, that in case of coherent precipitates, the dislocation can shear through the precipitate, and even in this case we would observe some amount of hardening. But suppose you are talking about incoherent precipitate, not only can the dislocation not shear through the precipitate, but it remain pinned at these 2 points of the precipitate, but nevertheless it can bypass the pinned segments by creation of loops, but nevertheless the original segment still remains, which can be operated further and further. And at some point of time, if this AB segment, the stress to operate this AB segment becomes too much, then there will be other segments. For instance, suppose you would start with the longest segment which can be operated first, then the shorter and the shorter, so that we now go to smaller and smaller pin segments which require higher and higher stresses to operate. And therefore this also would lead to a hardening in the material now, because now you are not allowing a free motion of dislocation. So both these mechanisms would lead to a hardening of the material, and therefore would constitute important from the material's behavior perspective. Next we consider dislocation free surface interaction. So far what we consider the dislocation stress field, as maybe if you consider the figure here, you can see the figure here, this is a dislocation stress field in an infinite body. Okay. But now suppose I have a dislocation sitting in a finite medium. So now you can see that this is my body on the left hand side. So this is my surface, free surface here, and to the left of this free surface is my body. The entire grey shaded area is the what you might call the vacuum if you like, now, or air for that matter. A dislocation near a free surface gets actually attracted towards a free surface, and this can happen because now the dislocation stress fields and in the presence of a free surface, the dislocation stress fields which have this left right symmetry is broken down. It no longer has this left right symmetry. So, in other words, if I have a dislocation in infinite medium, now this is my symmetry line, the line right the middle, okay. But this kind of a symmetry is broken down in the presence of an free surface, and now I can approximately draw my stress field in the presence of a free surface. So, now I have this is my free surface and I have a dislocation present here. So, now my butterflies would have a certain kind of a distortion in the presence of the free surface. So, in other words, now it does not have that left right symmetry which originally had around the dislocation line. Now, the dislocation is attracted towards this free surface because the free surface is a traction free surface. In other words, there are no tractions on the free surface. The force with which a dislocation is attracted towards an edge free surface is given by this formula right here, the F and it is called the image force, and it goes as 1 by d, where d is the distance of the dislocation from the free surface. So, this is for an image force experienced by an edge dislocation. So, this is an image force for an experienced by an edge dislocation. Similarly, a screw dislocation would also experience an attraction towards a free surface. So, what is the reason that this dislocation gets attracted towards the free surface? The reason is that actually if a dislocation moves to the free surface, it can relieve all its stresses and the energy of the system would be relieved except for the small step which is created. So, therefore, as a dislocation moves towards the surface, its energy reduces, and this is the reason that the dislocation is attracted towards the free surface. So, now on the other hand, suppose why is this called the image force is because this is a kind of force which you might call a configurational force. So, let me write down this name for you. So, this image force is a kind of configurational force. So, the image force is a kind of configurational force which attracts dislocations towards free surfaces. Now, as I said, the reason for the attraction is the lowering of the energy of the dislocation as it moves towards the free surface, and finally when it reaches the free surface, it creates a small step and all these stress fields are relieved. On the other hand, suppose I have a interface with a harder material, then that will be a repulsive. That means, instead of having a free surface, suppose I have a harder material on the other side of this interface. So, I have a dislocation here, and now this is my harder material, and I have a dislocation here. So, this is harder, this is my softer material. Then the dislocation would actually be repelled from this interface. So, I have my softer material on the left hand side, my harder material and dislocation sitting here going into the plane of the board. Then this dislocation would be repelled from this interface, while on the other hand, suppose you had a softer material or a free space here, then the dislocation will be attracted towards this free surface. Now, the reason this is called an image force is that suppose you want to calculate the value of this force, which is shown here below, you would actually construct an hypothetical negative dislocation located at a distance d, and now what I will do, I will artificially not only construct an dislocation of the opposite sign, but I will assume the material properties which are, for instance, g and nu on the left hand side is also maintained for this material g and nu. So, this hypothetical dislocation which I have constructed of the opposite sign, suppose this is now my positive dislocation, this will be negative dislocation, there will be a force of attraction between the positive and the negative dislocation, and that is why this is called an image force, because now I have constructed an hypothetical dislocation of at the same distance from the interface, and now I calculate the force between these two, and this dislocation is called the image dislocation, and hence this force is called the image force. So, a dislocation can also interact with free surfaces and interfaces with harder or softer materials. So, this is an important point to be noted, and if this force of attraction can exceed the Pearl stress, then the dislocation would automatically leave the crystal and go and sit on the surface. So, we will actually make a calculation later of the value of this image force and the kind of interaction it can and kind of motion it can lead to. an important point to be noted here is that as a dislocation goes to the free surface, it can actually distort the free surface as well. So, if my dislocation here for instance gets closer and closer to the free surface, and now assume that if my extra half plane is located at the bottom, this is my extra half plane. So, I have my extra half plane here, a dislocation, it is going towards the free surface, then as it goes suppose to a very close to a free surface. So, this is the free surface would be distorted, the presence of this dislocation would distort my free surface. This is my extra half plane. So, this can lead to a distortion of the free surface. So, this is something which is to be noted. So, the image force goes as 1 by d, that means it grows asymptotically as you approach the free surface. Now, dislocations can also, as I told you, this is a small deformation which I was talking about in this case, but presence of dislocations in thin plates or thin cylinders can actually lead to a larger kind of deformation, and that kind of a deformation often cannot be ignored as compared to the small deformation of the surface which I just pointed out. Now, suppose I have a thin plate. Now, I am talking about dimensions of the plate of the order of nanometers, and I have an edge dislocation sitting here. And suppose I have a flat plate originally, and then I introduce my edge dislocation going into the plane of the plate. So, my plate could be thin plate like this. Okay. What would happen is that the very mere presence of this dislocation, because now this dislocation is associated with an extra half plane, would lead to the bending of the plate. So, the plate would bend, because I have exaggerated the picture here, but typically if you have a plate of a few nanometer, it could even blend a few degrees. But you have to remember now this bending is coming because you are now introducing a dislocation into a flat place which originally was completely defect free. So, you can have what you might call deformations of this type, which are purely elastic deformations coming from the presence of dislocation. So, this is something which again is important to note. A screw dislocation, unlike the edge dislocation, leads to this twisting of the material. Suppose you had a cylindrical domain and you introduce a dislocation at the center of the cylinder, then it will actually lead to a twist in the cylinder which is coming from the presence of the dislocation. And so, this kind of a deformation is not the plastic deformation which you talk about, even though you can see that this is a large macroscopic deformation in the shape of the object, but this is an elastic deformation which is coming from the presence of a dislocation. Now, so far we were considering dislocations in some sense a negative light, because now dislocation is the agent which breaks the complete beautiful symmetry, the translation symmetry of the crystal, and therefore, it is an agent responsible for what you may call breaking the symmetry. It is a defect. So, often it seems to us that it is the antithesis of a crystal. The presence of a crystal and its defect is the opposite sense or in the opposite directions. But let us now consider a very interesting example, which is the constructive role of dislocations, and this role of dislocations comes in crystal growth. Often when you grow a crystal from low supersaturation, it is found that the growth rate is considerably faster than that calculated for an ideal crystal. So, this original calculation was made by Sir Frank, and it was found that this what you call disparity between the actual growth rate and the growth rate, assuming that you have a flat surface from which the crystal is growing. That means, suppose I had a flat surface like this in a crystal, a flat crystal like this, and now as I calculate theoretically that what should be the growth rate of this crystal by atoms coming and sitting on this surface, then this model would lead to a disparity with respect to the actual growth rates found experimentally by a huge amount, the exponential of the order of hundreds. So, therefore, there was a need for a different kind of mechanism which actually can lead to a growth rate which is commensurate with the experimental values, and the model proposed by Frank was this model which is shown in the figure, wherein you assume that a screw dislocation is terminating on the surface, and we just tilted a picture around which we saw before. And now, if an add atom or an atom shown in this picture in blue tries to come and stick to this surface, then it has preferential sites. For instance, and suppose it wants to stick here, then this site is for instance no different from this site, and it will freely diffuse from this side to that side. And so, you face the problem of what you might call the 2-dimensional analog of the 3-dimensional nucleation problem. So, you have to nucleate a surface step on this surface, but or a disk for that matter. But here the nucleation problem is got rid of, and now this add atom which is shown in blue here can actually come and attach to this core of the dislocation or somewhere here on the along the dislocation edge. The important point is that actually that this, if it comes and attaches here, this atom, this will not lead to the exhaustion of the the dislocation. So, it will keep on rotating, that means if more atoms come here, the dislocation will keep on rotating, and this will create a spiral around the central step. So, you can actually have a spiral coming out from here, and at no stage during this whole growth is this step created by the termination of the screw dislocation on the surface exhausted. So, many cases they have actually seen this experimentally, they observed this presence of the helical steps and leading to a faster growth later. So, we can see that the presence of a surface step created by a screw dislocation terminating on the free surface can help the growth of a crystal, and in this sense it is actually a constructive role of a screw dislocation in case of growth of a crystal. So, in this case the very growth of a crystal or the formation of crystal is being helped by a dislocation, and the important point is that this can actually lead to a beautiful growth spirals which never terminates itself and continue to operate itself, leading to actually growth of the crystal. So, this is the spiral staircase pattern which is created and looks extremely beautiful, and this kind of spiral staircases were discovered in the 1950s using interference optical microscopy. Now, we are close to the end of the chapter on dislocations, and what is the kind of a mental picture that we should leave with when you are talking about dislocations? There are many facets to understanding a dislocation, and there are very many ways we need to understand a dislocation, but the composite picture which we need to develop, putting together these individual pieces or these individual collage items, is what we have to carry at all points when we try to understand the dislocation. We need to understand obviously that it is a line defect. We need to understand that it locally causes a distortion of bonds and it results in a state of high energy for the crystal. It also leads to an increase in entropy of the system, because now there is a single a perfect crystal, for instance, exists in a single configurational state, but now in the presence of the dislocation can exist in many positions in the crystal, and therefore it will lead to an increase in the configurational entropy of the system. It is associated with the free volume of the core, and we have already noticed that can lead to the formation of the Quadrille atmosphere, and it can also lead to the diffusion of these interstitial species along the dislocation line, which is called pipe diffusion, and this pipe diffusion can have diffusivity values which are orders of magnitude away from the diffusivity through the lattice. We already seen that it is associated with stress and strain fields, which are now long range strain fields and stress fields, and these long range stress fields can interact with the stress fields of other defects, free surfaces, and as you can see that cause bending of the crystals themselves. And if you are talking about nanocrystals, then this bending can be very dramatic and actually can lead to an altered shape of the crystal, which is purely an elastic bending and not a plastic bending, even though the bending value is very large. Now, we need to worry about the interaction of this dislocation and other defects, and that leads to very interesting effects like the yield point phenomena. We have to understand the role of a dislocation in slip, which is perhaps very important role of dislocation. We need to understand it as a structural defect, apart from the fact that, and this role of understanding it as structural defect will take up a little more when we take up two-dimensional or low angle grain boundaries. For instance, now so far we have been talking of what you may call random dislocation, which can be present anywhere in the crystal, but it can also take up a structural role, and that we will consider when we talk about two-dimensional surfaces. And more important, and the starting point for all this was the association of dislocation with the translational symmetry of the crystal. So, we have many mental pictures of a dislocation, and when you put up all these individual phases together, we get a complete picture of a dislocation, and then of course we can worry about the motion of dislocation, interaction of dislocation, etc., which we considered at the beginning of the chapter. So, now let us ask us a few questions which are very important. The first question we can ask ourselves: why are dislocations non-equilibrium defects? I just now pointed out that like vacancies, presence of dislocations increases the configurational entropy of the system. If this is going to lead to an increase in configurational entropy of the system, why is it that vacancy is a stable equilibrium defect, or can be in a certain concentration a stable equilibrium defect at any positive Kelvin temperature, while dislocations are non-equilibrium defects? So, we start with the familiar equation delta G equal to delta H minus T delta S, and here at any positive Kelvin temperature, if a system has some configurational benefit, then it can be stabilized by the presence of, for instance, in this case, a defect. So, we have already seen that this entropy change is positive in the presence of dislocation, the configurational entropy given by k ln omega. However large a value of delta H may be, suppose it costs a lot of energy, positive value of delta H to put a defect, but if there is even a smallest of the benefit coming from the presence of that defect, then there will be a temperature at which this will be offset, this term will go to 0, and after that, after even higher temperature, the term will become negative. So, if there is an entropy benefit, then there will be a temperature, some temperature at which this delta G will become negative, even if the enthalpy cost is very high for that configuration, the configuration with, for instance, a defect. Now, actually when I am talking about configurational entropy, an important point to be noted that this configurational entropy includes positional, electronic, rotational and vibrational multiplicity of states, but here for instance we are now dealing with only positional states to make matters simple. So, there is the larger consideration we need to take often, but we are taking up a sort of a restricted thing of importance here. In the present case, the energy cost we know goes as GB square per unit length of the dislocation line, and we have seen that the configurational entropy benefit is also there, because now the dislocation can exist in many equivalent states within the positions within a considerably large crystal. It is a very small crystal, things are different, but if you have a large crystal, then there are many equivalent states within which the dislocation can exist, leading to an approximately equal state of energy. Now, this equation tells us there must be a temperature where the dislocations can become stable in the crystal, but the unfortunate point is that this temperature calculated is above the melting point of all known materials, and therefore dislocations are not stable defects in crystals. It is not that this equation cannot become negative, in other words it is not that the dislocations cannot be stabilized theoretically, it is just that as a practical difficulty that all crystals known would melt before a dislocation becomes stable in the crystal, and that is why that we call dislocations are non-equilibrium defects, not because dislocations cannot give us an entropic benefit. Dislocation can give us an entropic benefit, and therefore this part of the term would always be in favor of us at any finite temperature, while this term is the one which is opposing us. So, we have to understand that dislocations are non-equilibrium defects from this perspective. The second question we asked is that the most important thing we started off the role of dislocations was its role in weakening the crystal, but now we will have a little more deeper perspective on this, and we will ask ourselves the question, how are crystals weakened. The first thing is the presence of dislocation, which is a line defect which weakens the crystal, and we already seen that this weakening in the shear stress is of the order of a few orders of magnitude. Okay, that is an important thing. So, a few orders of magnitude. Now, this problem of shearing the entire crystal, which is now shown here on the left hand side, suppose I had a perfect crystal and I lead to its shearing. So, this is my problem of shearing the entire crystal. I broke down into, and I even gave an example of the carpet analogy. Therefore, I broke it down into a line defect, which is the dislocation moving through the crystal and creating a small step. So, this was the carpet analogy. So, by shearing the entire crystal, now I am breaking down the problem line wise, and those lines moving and giving me a step of B. So, but there is a further reduction in this problem, a dimensionality possible, which can lead to a further weakening of the crystal, and that is what is called the kink pair mechanism. So, how does the kink pair operate? Suppose I had a perfect dislocation line, I can have a kink in the dislocation line, and I am now talking about a double kink. And as there was a slide here that these kinks can be created by thermal fluctuations. So, thermally activated, you can have a double kink formation. And I pointed out that what is a kink? A kink is a defect in a defect. A dislocation is a line defect in the crystal, a kink is a defect in the dislocation line. So, these are now thermally formed kinks. Under the application of external stress, these kinks can actually move outward, as shown in this slide here on the right hand side. So, kinks can move out, and when these kinks leave the crystal surface, so you can see that it moves out a little bit more, then it moves a little more, and finally when it leaves the crystal, you can see in this slide. So, here it is moving outward, moved out a little, moved a little more, and finally when it leaves the crystal, it has actually moved the dislocation by a small b. So, when I was trying to shear the entire crystal, I could move the entire crystal and create a small step, or a step of n times some atomic parameter like Berger's vector, but I could break down the problem into moving of a dislocation line creating that Berger's vector. But further, I could break down the motion of a dislocation line itself into formation and motion of kinks. So, this is now a second order problem, and this can be found in certain BCC metals as shown here. can be found in BCC metal, and for instance germanium could also have these kind of mechanisms, and this would lead to the motion of a dislocation below the Pearl stress, and therefore this dislocation can nucleate a kink, and therefore the kink can move, and this whole dislocation can move by Burgers vector B. So, this can be thought of as a sidewise roll within the roll of the carpet itself. So, now this is a 3-dimensional perspective of the kink. So, this is very interesting, that not only can I shear the crystal, make the crystal weaker by the presence of dislocations, but I can even further weaken the crystal by the presence of these kinks in the dislocation line, which is a defect within a defect, and now that defect can lead to the weakening of the crystal. So, you can see that the kink pair has been nucleated, the kink pair moves and finally moves the dislocation by this distance, and further again you can have a kink pair nucleation leading to the motion of dislocation by a further B. So far what dislocations we were talking about were random dislocations, or sometimes as the term is used it is called statistically necessary dislocations, but we will avoid the use of some terms like geometrically necessary dislocations in this context, and we will call these other kind of dislocation as structural dislocations, and we will distinguish them from the statistically present dislocations. A structural dislocation may be associated with the boundary, and hence their role in plasticity may be very different from the random dislocations. It is very important to note that once a defect is a structural defect, and one of these examples we already seen in the case of semi-coherent precipitate, the dislocation present at the interface is a structural defect there. And examples of structural defects include dislocations at low angle grain boundaries and dislocations in semi-coherent interfaces. So, you could have interfaces associated with structural dislocations, or a grain boundary associated with structural dislocations. Now, what is the kind of role that they can play, these structural dislocations in terms of the geometry of the crystal? They can accommodate tilt between two crystals. So, suppose I have two crystals, and for instance in this case they could be the two crystals with just a misorientation. So, this could be a grain 1 in a crystal, and this could be a grain 2 in a crystal. So, both of them are the same material on either side, but now they have been misoriented by a small angle. When I mean a small angle, I typically mean an angle about less than about 10 degrees or thereabout. So, these dislocations can actually accommodate this tilt, and we will see later on when we do 2-dimensional defects that how this is actually accommodated, but for now we need to remember that these structural dislocation can accommodate tilt. We can actually twist two crystals, a crystal 1 for instance in the top, and assuming a material of the same type, grain 2, and I can accommodate a small angle twist of crystal 1 with respect to 2. Now, this is my angle of twist, and I can twist my crystal 1 with respect to crystal 2, and this twist can be accommodated by, in this case, screw dislocations. Tilts are accommodated by edge dislocations. So, this would be my edge dislocation, and this would be my screw dislocation, which would accommodate the twist. And finally, I can have suppose I have two different crystals, a crystal 1 with a smaller lattice parameter sitting on a crystal 2 with a larger lattice parameter, then this misfit between these two crystals can be accommodated. Related to this would be that now if this crystal is epitaxially grown on this crystal, then I would find that this would expand, this crystal, the green crystal would expand to sit on the blue crystal, and therefore they would have the same size. This mismatch would be actually, that means that I will have to make the crystal, green crystal larger, pull it and fit it on top of this blue crystal, and therefore there will be misfit strains, and when this crystal epitaxially grows a little larger, then this misfit strain can be accommodated by the presence of dislocations on the interface. So, you will have a lot of interfacial misfit dislocations. So, though we have not gone into the details of all these aspects in this very slide, but it is important to remember dislocations can play a structural role, and when they play a structural role, their role for instance in the behavior of the material like plasticity would be different from those dislocations which are randomly present in the material, and the kind of structural role they can perform is they can accommodate tilt between two crystals, they can accommodate twist between two crystals, and they can also accommodate a mismatch in lattice parameters between two crystals. Of course, there could always be a combination of all these effects, like could have a tilt comma twist or a misfit comma twist, etc., which also can be accommodated by the presence of dislocations, but these are nice, interesting extreme examples which illustrate the structural role of dislocations in materials. And this is very important to keep in mind. Suppose there were this misfit or a twist between two crystals have been accommodated by screw dislocations which are now present along the interface, these dislocations would have a tendency not to leave the interface, because if they leave the interface then they are going to alter the angle of twist. Another important fundamental aspect which we have seen, just I would like to mention in one line, is that often it is thought is that the question we are asking ourselves is that what determines a Burgers vector. So, the answer is that if you already have a dislocation in the crystal, then I can use a Burgers circuit to determine this Burgers vector. But what actually determines the Burgers vector is the crystallography, and therefore, if somebody asks you a question that what determines the Burgers vector, it has to be the crystallography, because the Burgers vector is the shortest lattice translation vector for a perfect dislocation. So, this aspect has to be kept in mind. Let us take a few simple examples, and maybe I will just gloss over these a little fast, but what students can do is actually keep these slides in front or try to parallelly solve these problems, because these are nothing but problems in geometry, and the concepts involved are very, very simple. So, the question we are asking ourselves here is that in a cubic crystal, a dislocation line of mixed character lies along the 1, 1, 2 direction. Burgers vector of this dislocation is half 1, 1, 0. What is the edge and screw components of the Burgers vector? What is the slip plane? So, we have given that the Burgers vector is B vector is half 1, 1, 0 and the T vector is 1, 1, 2. So, these two are given to us. Now, we know that whatever component, if I resolve the B along T and perpendicular to T, if B is parallel to T, that is the screw component, and if B is perpendicular to T, that is the edge component. So, let me see the Burgers vector here. This is now my B, and now this is my T vector, which is shown here in the 3-dimensional view. Okay. Now, this B vector can be resolved into a component parallel to T and a component perpendicular to T. So, I need to know the two directions, the direction of T and the direction of T perpendicular. So, the subscript perpendicular implies it is the direction perpendicular to T. This is all the question I am asking, and we also know that the plane containing T and B is my slip plane. So, it is obvious in this case the slip plane is 1, 1 bar 0. And now I am not asking for a general family of planes, but a very specific plane which contains this T and B, therefore, I need to write the very specific plane which is 1, 1 bar 0. And in this whole problem, vectors are shown by arrows above, and these kind of hats represent unit vectors along those directions. So, B is 1, 1, 0, therefore, the mod of B, the value of B is root 2 by 2. I can calculate the square root of 1 square plus 1 square plus 0 square by 2, this is root 2 by 2, which is 1 by root 2. B hat is 1 by root 2, 1, 1, 0. Therefore, the unit vector along the B direction is 1 by root 2, 1, 1, 0. The T vector is 1, 1, 2, which is given to us. The modulus of the T vector is root 6, the length of this vector is root 6, and T hat is 1 by root 6, 1, 1, 2, which is the unit vector along the T direction. So, now in this picture, which is now the 1, 1, 0 plane picture, you can see that this is now my B vector, horizontal direction, the T vector which is along connecting O and C, and the T perpendicular direction is also shown in this picture. So, now if I want to calculate the slip plane, which is the plane containing B and T, I can apply Wies zone law on the fact that it lies on it contains 1, 1, 0 direction and the 1, 1, 2 direction both, and I apply Wies zone law assuming that the slip plane is HKL. Therefore, H plus K is 0, giving these two H plus K is plus 0 is equal to 0, and H plus K plus 2L is equal to 0, assuming that the 1, 1, 2 direction, the T direction also lies on the slip plane. This leads us to the fact that L is 0 and H equal to minus K, and I can write my slip as H bar 0 or 1, 1, 0 in terms of least indices. For the screw segment, we know that the B is perpendicular to T, and for the edge segment, the B is perpendicular to T. Now, if you look back at the figure, we can calculate the angle between the theta angle between the T vector and the B vector, and that is nothing but 1 by root 2 by root 6 by 2 from pure geometry, and that turns out to be 1 by root 3, and this gives me a theta value of 54.73 degrees. So, this angle between my B vector and T vector is 54.73 degrees. Now, if the direction perpendicular to T is T perpendicular is UVW, this direction lies on 1, 1 bar 0 plane, the slip plane, and is perpendicular to the T vector. So, this is obvious. Now, I can again apply waste zone law assuming these two conditions for the UVW direction, which is now the direction perpendicular to the T, and this for applying this on this 1 1 bar 0 gives me u minus v equal to 0, and applying it to the condition that is perpendicular to T gives me, which is now the T vector being 1 1 2. Therefore, now my condition will be u plus v plus 2 w equal to 0. This gives me that u has to be minus w and u equal to v, and therefore, I can write my Miller indices of the T perpendicular vector as u bar, u bar, which is nothing but 1 1 1 bar. So, my T perpendicular is 1 1 1 bar and T perpendicular cap is 1 by root 3 1 1 bar. So, now this direction is 1 1 2, and the direction perpendicular to my T vector, which I call the T perpendicular, which also lies on the slip plane, which is the 1 1 bar 0 plane, has indices of 1 1 1 bar. Therefore, I can write down my B parallel and B perpendicular, knowing the geometry that B dot T is has the value right here. I can calculate as the dot product between the B vector and the T vector, which is 1 by root 6, and therefore, my B parallel is mod B into the T vector, which is 1/6 1 1 2. So, my B parallel component is 1 by 6 1 1 2. The perpendicular component, again I can calculate the modulus, I can calculate by taking the dot product between the B and the T perpendicular, which comes out to 1 by root 3, and I can write down my B perpendicular vector as the mod of the B perpendicular vector along the direction of the T perpendicular, and therefore, it is 1/3 1 1 1 bar. So, now I can find out, given any kind of geometry, the edge and the screw component to any edge and screw character to any curved dislocation line, or for instance, a straight dislocation line, of course, having which is constant, which does not change its character. So, this is not really a problem going beyond actually the very concept that for the screw component you have the Burgers vector parallel to the T vector, and for an edge component the Burgers vector is perpendicular to the T vector. The remaining is nothing but simple vector algebra and also invoking the waste zone law. This is all we have done in this problem to identify the slip plane and the parallel and perpendicular components of the Burgers vector. Now, we come across an interesting case, the case that if it is very clear that suppose I have a crystal and I have a dislocation lying in the crystal and I apply an external shear stress, that the dislocation will move when the shear stresses crosses the pulse stress. So, this part is not very surprising. That means there is an external agent driving the dislocation line, but we are asking ourselves a question, even in the absence of external agents, can a dislocation move? And obviously, there are certain nice examples of this. For instance, suppose I have precipitates, they are associated with stress fields, and if these stress fields are large enough, then the dislocation line can move. But the most interesting example of all this is perhaps the case wherein a dislocation is present near a free surface or in a nanocrystal. Suppose a dislocation is present near a free surface, we have seen that it is attracted towards the free surface. If this distance d is very large, the force would be very small, because now the force is proportional to 1 by d, and therefore, it will be too small to move the dislocation. But if it is very near the surface, or if it is present in a nanocrystal, suppose a very small crystal, therefore, if these dimensions are the order of nanometers, then the dislocation has many surfaces to which it will be attracted, and the resultant of all these forces would determine if the dislocation would actually end up moving in this crystal. So, let us ask this question, that if a dislocation is present in a near a free surface at a distance of about 100 b, so this is a distance of about 100 b, then will this presence of this image force, that means the presence of this free surface itself, move the dislocation towards it. Okay. I mean, now assume an aluminum crystal. An aluminum crystal has a Burgers vector of 2.86 angstrom, and the shear modulus is 26.18 gigapascal. The Poisson's ratio for aluminum is about 0.348, and the lattice parameter of aluminum is 4.04 angstrom. Now, the important question we are asking, is this force experienced by this dislocation in the presence of a free surface, that is now a semi-infinite body, sufficient to move the dislocation, given that the Pearl's force for this, which is nothing but the Pearl's force is nothing but the Pearl stress into the Burgers vector, and the Pearl's force is 2.5 into 10 power minus 4 Newton per meter. I assume a Pearl's force of what? 2.5 into 10 power minus 4 Newton per meter. So, now what is the image force, assuming that this is an edge dislocation? So, this is given an edge dislocation here. So, the image force is minus GB square by 4 pi into 1 minus nu into d. If it was screw dislocation, this 1 minus nu factor would be replaced by 1. An important point to note is the negative value here. The negative value tells you that it is actually attracted towards the free surface. So, the image force given the fact that now the distance is 100 b can be calculated by plugging in the value of g, the Burgers vector b, the value of the Poisson's ratio and the distance from the free surface, and it turns out to be 9.1 into 10 power minus 3 Newton per meter. Clearly, the image force is greater than the pulse force. That means the dislocation will spontaneously move and move to the surface and leave the crystal. So, this is in the absence of externally applied stresses, and suppose I am talking about a nanocrystal in which there are many free surfaces to which the dislocation can be attracted, then this implies that a nanocrystal can become completely dislocation free even without the application of external stresses, because now the dislocations would be attracted to free surfaces, they would move to free surfaces if the Pearl stress is exceeded, and as you know, in a nanocrystal the distance between a dislocation and the free surface is going to be very small. Therefore, it could happen that at very small sizes, and in fact it does happen that, for instance, in aluminum crystals which are about 50 angstroms in 50 nanometer in diameter, then dislocations spontaneously leave the crystal and the crystal becomes completely dislocation free. So, this is a very interesting problem we have solved here, that crystals can actually become spontaneously dislocation free without even application of external stresses, or the reduced problem being that dislocations can actually move even in the absence of externally applied stresses. So, if you had a free surface like this, then there will be a region very close to the free surface wherein my image stresses will be so large that it can support no dislocations, and all dislocations in the region would come and sit on the surface. Given that, of course, that these dislocations are glissile, and also the fact that they face an image force greater than the Pearl stress, and assuming that the Pearl stress is not too large. So, this is a very nice interesting example I considered, and with this we come to the end of the topic on dislocations, and the next topic we take up is a topic on two-dimensional defects, and that will be and wherein we will again invoke some of the concepts we learnt in this chapter.